everyone, and welcome to lesson 29.2, which is going to talk about converting polar equations and rectangular equations into the alternate forms. Today's lesson starts on page 397 in your Springboard textbook. So in the first couple of examples, we see some examples that we've already talked about in prior lesson, and we're also going to start talking about converting more polars to rectangular formats. Now, something that you definitely want to have written down is that r equals square root of x squared plus y squared, and then what x equals and y equals, because we are going to be making a lot of substitutions today using those. You may also want to have that r squared equals x squared plus y squared, because sometimes when we have just things in terms of r squared, it's easier to just make this substitution of x squared plus y squared. It just comes from this piece here. So notice here, going back to kind of some stuff we talked about in Unit 4, we can change secant theta into 1 over cosine theta, multiply both sides by that cosine theta, and then the r cosine theta we replace with an x for that vertical line of x equals 4. And then some of the other examples we see here in A and B, we actually talked about in the prior lesson, because remember, anytime we just have r equals 10 or a value, it's a circle centered at 0, 0, and then the radius value is 10, so r squared is 100 in rectangular form. And we also talked about how whenever we have these tangent problems, theta problems, if we take the tangent of both sides, we know this turns into y over x. Tangent of 135 is -1, and when we multiply both sides by x, we get this line, -1x for -x. And then last but not least, example C is very similar to the example A up above. We could change cosecant of theta into sine of theta. I know you probably thought all these had gone away, but basic one there of converting. And then multiply both sides by that sine of theta, we get 8. And then last but not least, this r sine theta, we know we can replace with y, and we have a horizontal line, y equals 8. Okay. Now, if we look at this line here, this actually is going to also be the equation of a line similar to what we had up above, but it's not going to be a vertical line or a horizontal line like we saw with the examples up above. So when we start converting for this one, the process is kind of similar to what we did above. We're going to want to multiply both sides by this denominator, right? If we can get this out of the denominator to start working with it, we can cancel on the right-hand side that. And then on the left-hand side, we have r times 3 cosine theta minus 6 sine theta. Okay. Now, what's going to happen is we want to distribute that r to both pieces, because right now we have that out front here. And when we distribute that r through, because right now it just equals 2 since these canceled, we now are going to have 3r cosine theta minus 6r sine theta. And we know from up above, again, they're very important, we can replace the r cosine theta with an x and the r sine theta with a y. Oops. And now we see starting to form that equation of a line. So 3x minus 6y equals 2. And officially, to be able to tell a little bit more details about this line, we like it in the y equals format, slope-intercept form, so we can start telling a little bit more about this line. So bring over the x value, divide everything by the -6, we get y equals 1/2 x minus 1/3. So we could start talking about this line specifically with a slope of 1/2 and a y-intercept of -1/3. Writing utensils not cooperating here. Okay. Now, as we flip to the next page and look at example B here, we start talking about more examples with converting these. Now, in this one, we are converting, again, back to rectangular, and again, keeping these handy. Now, notice here, if we multiply both sides by an R value, what's happening is everything gets an R, and this R squared can be transitioned to X squared plus Y squared, hence why I said having this as part of your list of things is often very helpful. And we can also then make the substitution with the R cosines and the R sines to be X's and Y's. And now it just turns into the handy dandy equation of a circle that we were dealing with a lot in Unit 5A, so that we can convert these, right? So again, first tactic here is to multiply everything by an R, because now we have R squared equals negative 24 R cosine theta plus 10 R sine theta. So everything got an R, and then the R became R squared, obviously. Now we can make that transition. This is now going to be X squared plus Y squared for our R squared. And then we're also going to be able to substitute in here for R cosine and R sine, X and Y. So we have negative 24X plus 10Y. And now as we bring everything over to one side, we have X squared plus 24X. We'll have to complete the square on that. Plus Y squared minus 10Y. I'm going to have to subtract that over. Complete the square on that. And we will be adding those blanks to the other side. 24 divided by 2 is 12. Squared is 144. And on the negative 10 divided by 2, negative 5 squared is 25. So as we factor, we have X plus 12 quantity squared, Y minus 5 quantity squared when we factor this piece, and then all of that's going to equal 169. Okay. Now, as we look at this information, then we're able to describe these polar formats a little bit easier, because what's happening is that we see when we have the polar, we're much better at identifying things such as our center being at 3, negative 2, and our radius value being the square root of 25, which is just 5. Okay, so that rectangular form, again, then can help us quickly identify some pieces of information that ordinarily would not have been as quick to identify. Similar here, then we can do that with converting and then analyzing number 3. Okay. All right, now our last types of examples that we have are on page 399, and we have examples C and D. So this time we are converting to polar form from our X and Y rectangular form, right? So we know, again, those substitutions, anytime we can substitute in R sine and R cosine, we're going between those forms. So in this case, we're substituting in R sine for Y and then R cosine theta for X. Now notice that was squared. So the square then is going to get distributed to both pieces. And what we're going to do is we're going to group this, move everything so that the R's are together. So actually one R will cancel with the other. And then we're going to leave the R by itself, because again, our goal, anytime you're trying to get to a full polar form, is you want it in the form R equals, and then we're going to simplify. The other type of problem we are going to see is, again, utilizing this. Now be careful here with the 2y squared. That's like saying y squared plus y squared. And the reason it's helpful to break that up is because when you break this into just y squared plus y squared, we can convert, use the x squared plus y squared is now r squared. And then we can take this y squared and make it r squared sine squared. Because really, if you want x squared, that's like saying r squared cosine squared. And y squared is like saying r squared sine squared. Not necessarily something you have to write down, but it might be useful to you to remember, especially as you're beginning with these. Okay. And now group these up in GCF, the r squareds. We can factor that out and divide everything over, because again, whenever you want polar form, your goal is to get just r equals by itself. Okay. All right, so we have these last couple of examples here. So the first one, we have y squared equals to x. So again, we're going to start by converting the fact that y squared is our sine theta, quantity squared, and then equals 2x, which we're going to substitute in our cosine theta for that x. So this now becomes r squared sine squared theta, and then equals 2r cosine theta. One of the r's on the left-hand side will cancel with the only r on the right-hand side. And then again, our goal is to get r by itself. So we're going to divide away this sine squared theta from both sides. And we're left with just r equals, is this canceled? And then 2 over cosine times sine squared, which really is like saying sine times sine. So cosine over one of the sines can be rewritten as a cotangent theta, right? And then 1 over sine is cosecant theta. You didn't think those reciprocal functions were going to come back, but here they are. Okay. Next example we have is converting here. So again, we're going to substitute in for our x value, our cosine theta, and then for our y value, our sine theta. And then that's going to equal 3. And again, what we're going to do is both of these have an r in common. Okay, so we're going to take out that GCF, and we're left now with 4 cosine theta plus 5 sine theta equals 3. And then last but not least, to get r completely by itself, we're going to divide away the piece in parentheses, and we get our equation of the line in polar format. And again, this kind of goes back to what we did on that first page. Remember when we converted here, this was initially, looking like very similar to that answer we just got, and we were able to convert it to rectangular to get the line, and now we're kind of going that opposite direction where we had a line to start, and now it's back into this format. So you start seeing in polar form what our line equations of lines are going to look like. And when in doubt, you can always graph this and see like, oh, like what does this look like? So we have 4 cos theta and then plus 5 sine theta. And then I'm just going to zoom 6. But we see, this line kind of coming in here. Obviously, it's looking a little weird at the moment because of the window, which we'll talk about in the next lesson, needing to maybe go around a couple more, maybe to 720. Which again, this will be next lesson. But you can start seeing again that line. All right. Last but not least, our final example. We have here one where we have this 2x squared. So I'm going to start by rewriting this as actually x squared plus x squared, and then plus the y squared plus the 3y equals 0. Because what I can do is I can make this substitution in for the one for x squared plus y squared. This is now going to be r squared. And then we can substitute in for this x squared. We're going to say that this is r squared cosine squared. Okay. And then plus the 3 y would really be 3r sine theta. Okay. And then equals 0. Now what we're going to do is we are going to move over this piece here because it doesn't have an r squared. We're going to leave the 2r squared components on the left-hand side, and we're going to subtract to the other side this 3r sine theta, because what we're going to be able to do then on the left is take out this GCF of r squared and be left with 1 plus cosine theta. And now that we have that factored out, we can cancel this r on the right with one of our r squareds on the left. And then last but not least, get r completely alone by dividing away our parentheses. We have 3 sine theta divided by the 1 plus cosine theta that we had in parentheses. Oops, excuse me. This was cosine squared. I dropped my squared. Don't do that. That's still cosine squared through this whole thing. So sorry. So keep the cosine squared. Cosine squared theta. Okay. All right, and that's where we're going to leave that one. All right, now we will obviously definitely be working more with this in class, and then we will actually move into talking about number 4 in the next lesson. It's kind of a change up and transition as well to the next lesson. So we'll talk about that later. Thanks for watching, and have a great rest of your day.